Hello everyone, welcome back. In this video, we'll be discussing about the last problem of today's weekly contest, alternating groups 3. The problem is a bit difficult, so the video can go a little longer, but if you stick to the end, I'm very sure you will be able to understand everything that's there in this problem and also be able to code this entire solution by yourself. With that, let's get started. The problem states that you're given some red and blue tiles arranged circularly. You are given array colors and a 2D integer array queries. So color of I denote the color of the ith tile. If it is 0, it means the tile is red, otherwise the tile is blue. Alternating group is a contiguous subset of tiles with alternating colors. You have to process two type of queries. First is, given a size, tell me how many alternating groups with this particular size exist. Second, given an index and a color, change the color of the given index to this particular color. Now, for query of type 1, you will be returning an integer. So for every query of type 1, you need to return an integer and form an array out of it and return this in the order, right? So let's take an example. Let's say the color says 0, 1, 1, 0, 1. So this is how it would look like. 0 is red and 1 is blue. So this is how your tile arrangement look like in the circular fashion. Now the first query is 210. Basically it says change the color of the first tile to 0. So the color of the first tile is 1 or blue. We have to change it to 0. So if you change it to 0, this is how it would look like. Second query says 1, 4. Basically it says count the number of contiguous sequences of tiles with alternating colors of size 4. And if you see this 1, 2, 3, 4 form a alternating sequence color of size 4. So that's 1, 2, 3, 4, 0. Again, alternating colors with size 4. So overall, you have two alternating sequences of length 4 in this entire circular array. So answer here is 2, right? So hope the problem statement is clear. Now before tackling this entire problem, let's tackle a smaller version of the problem which says we don't have update queries at all. We just have to figure out, given a size, give me the total count of alternating groups with that particular size, right? And we have to do it efficiently because the number of queries are huge. It is 5 into 10 to the power 4 and the color or the number of tiles we have is also huge. So let's try to solve this part efficiently first before tackling the complete problem. So first thing is we have to figure out alternating sequences of alternating colors, right? So because this entire array is circular, this particular sequence is a valid sequence. But if you consider this entire thing as an array, this sequence is something you will not be able to come up with because this covers the last element with the first, second and third element of the array, right? So there is a small trick. Whenever circular array is given to you, you can simply repeat the entire array twice and you will be able to get all particular sequences. So here, let's say the array starts from this index. So 1, 0, 1, 0, 1, 1, 0, 1, 0, 1, and you can simply repeat this entire thing again, 1, 0, 1, 0, 1. Now, if you think about it, you have every possible sequences. So you have all the sequences within this array itself, right? Let's talk about the sequences of length 3. So you have all the sequences here, and this sequence is also there now. What this sequence denotes? The second last and the last element with the first element, second last and the last element with the first element. So that's a valid sequence in the circular array, right? Similarly, this sequence also exists, which is last element with the first and the second element, last element with the first and the second element, right? So basically, if you simply repeat this entire thing twice, you will be able to get all possible sequences. And notice that you will not be using the last element. Again, this depends on problem to problem, but for this problem, we'll not use the last element because using the last element would, like, total length of the sequence that can be asked is of length colors or dot length minus 1. So this will be the largest sequence that you can have. You can't have greater than that, like the length of the sequence can't be greater than that. So if you take a sequence of length 5 starting here, that would simply mean that you are taking this entire array which is already considered here, right? So in simple words, we will not consider the last element for this particular problem, right? We'll repeat the entire thing except the last element. Now we know how to enumerate all the sequences. We now need to count the total count of sequences of the given length. Let's say the current query length is 3. We need to count the number of alternating sequences of length 3. What's the brute force way? The brute force way would simply be try and iterate over every sequences of length 3. So this is the first sequence of length 3. Is everything alternating here? Answer is yes. So increment your counter. Is everything alternating here? Answer is yes. Increment your counter. Is everything alternating? Yes. Increment your counter. Is everything alternating? No. 0, 1, it should be 0, otherwise it should be 0, but it is 1. So will not increment the counter. Is everything alternating? No, because 1 after 1 it should be 0. Is everything alternating? Yes, but will not consider this. Why? Because it's starting at this index, which in other words would simply mean that we are starting here. So we have already considered this while considering the original value. So we'll not consider anything or any array or any sequence that starts after this index, right? So any sequence that starts after this index will basically mean we have considered this already on the original array, right? So in this particular scenario, we got 3 sequences of length 3 which are valid, right? Now what's the time complexity of this entire brute force approach? What you're doing, you are iterating over a sequence, all the sequences of given length. So number of sequence of given length would be 2n minus l, like of this order, not exactly this, it will be plus minus 1 or something, but of this order, right? And for each of the sequence, you are iterating over the sequence to figure out whether it is valid or not. So overall, you are taking 2n minus l multiplied by l number of lengths, and l can in worst case be n. So overall, this entire thing is n square. So for each query, you are taking order n square time in worst case. You have q number of queries, so overall complexity would simply be q n square, which is very worse. You can't afford q into n as well because q and n both are used here, right? So we need to optimize this. So let's try to remove one of the n from here, right? Because that would that might help us understand what exactly we can reduce. So one n was coming from the fact that you are iterating over every sequences, and second n is coming from the fact that you are, for each sequence, you are checking whether it is alternating or not. Now can you remove this n? Like removing this n is harder, because if you don't iterate over every sequence, you need to come up with some other technique to count the valid ones. Let's figure out first, can we do some pre-computation to determine whether a subarray is valid or not? If you are able to do this, then this n can be removed. So I would encourage you to pause and try to think for a moment. The answer is yes. Basically, what you can do, you can simply iterate over this entire array beforehand and maintain up till what the array is valid. So in this case, you will say, okay, starting from here, everything up till here is valid, right? Similarly, after that, starting from here, everything up till here is valid. So you have 2 different valid subarrays here. And now if I ask you for a sequence, is this sequence valid? You can simply check its L and its R and simply check your valid subarray. If it is completely overlapping with any of them, it's a valid subarray. It's a valid sequence, right? So you can do this in 2 pointer like fashion, and this order n can be removed to order 1 by simply checking the corners of this array with the original correct sequence array, right? So the complexity now is order q into n. Again, this is not enough because n is also huge, so we need to optimize this as well. How to do this? Basically, removing this n would mean that we can't simply iterate over every possible sequences of given length q. We need to do something smarter. How to do this? The answer is, like, you already know us that there is a contiguous group of 5 that is valid, and because this contiguous group of 5 is valid, in this contiguous group every sequence of length 3 will be valid, right? That I know. So why even I would iterate over every sequence of length 3 here? I will simply figure out how many sequences of length 3 is possible with length 5 and add that to my answer, and that will be valid answer because I know I would have done the same thing if I have iterated over every subarray one by one, right? So what we are saying is, let's say there are two contiguous sequences. Like, let's talk an hypothetical scenario where there are two sequences. Now if you iterate over these sequences one by one, let's say you first talk about this sequence, is it valid? You will check, okay, is this completely overlapping with any of them, or is it completely inside any of the valid sequence? Answer is yes, so you'll increment the counter. Now you'll check this one, is it completely overlapping with any of these? Answer is no, so you'll not increment the counter. Then you'll check this one. Basically, whenever it is crossing the boundary, the sequence will not be valid. Sequence will only be valid when it is completely inside one particular boundary, and we can take that advantage and say that, okay, we know that only sequences that can be valid is inside this or this. So I can simply take this. Let's say this is of length 3. I will simply check how many sequence of length 3 is possible inside this length 3 sequence. Similarly, this is length 5. I will check how many sequence of length 3 is possible inside this sequence of length 5. And I can simply sum them up to get my final answer. So in this case, number of sequence of length 3 possible inside this would simply be 1. And in this, number of sequence of length 3 possible here would be 3. And like how 3 and 1, basically it's you can simply take L minus Q plus 1 as your formula. That many sequences will be there inside a length L sequence, right? So the overall complexity is now reduced to order Q multiplied by number of valid sequences. Let's call it number of valid sequences. And this valid sequence you can compute beforehand. You can simply say, okay, I will iterate over the entire array, check the contiguous sections which are valid, and once I have the contiguous sections with me, I will simply, like while answering, I will simply go over each of these contiguous sections, count how many sequences of length 3 is possible, and sum them up to get the answer, right? So this is better than the previous one, but it's still in worst case q into n. Why? Because in worst case it can happen that it is 1 1 1 1, everything is same. So every element itself is a group and you can't go beyond that. So overall you need to check for n different groups in that scenario, and the complexity would again be order q into n. But the average time complexity is very less here, because if there are contiguous groups, you, instead of iterating over these 5 elements, you will simply iterate over one element, which is 5, right? Now we have reduced this, but we need to do better. How to do better? I would again encourage you to pause and think about it. So notice what we have. We have 3 and 5. We need to figure out, okay, for 3, apply this formula, get a number. For 5, apply this formula, get a number, and sum both the things up to get the final answer, right? Again, there are some edge cases. We'll come to edge cases in a bit, but for now, let's talk about that particular scenario wherein we have a formula and we just simply need to apply that formula to get the answer. So let's say this is your array. You need to get the answer for 3. So the formula is, you go over each of these elements, check for, apply the formula and get the answer. So for this one, you will get 2. For this you will get 3. For this 4 minus 3 plus 1 again 2. 5 minus 3 plus 1 again 3. 2 minus 3 plus 1 you will get 0, but if it is 1 you will get minus 1 as well. Basically if it is less than the length you will simply put 0 here instead of putting anything negative. Now for this one you will get 2, and for this one you will get 1. Now notice, if it is just about applying the formula, you can do something better here. So let's say the formula is again L minus Q plus 1, right? And this is Li because the length is different here, right? And you need to simply sum them all up for every I. So what you can simply do, you can just like bring apart the summation I Li minus n into Q plus n, right? So this is your final formula as well, and the summation Li will simply be the sum of every element here, right? But this formula will not give you the correct answer. Why? Because there could be elements which are less than the length of Q itself, right? So let's say this is 1. In that case, if you do L minus Q plus 1, this will come as minus 1, and that is something you can't use here because that would negatively impact your final answer. So for anything which is less than the length, you have to put 0. So it's actually not Li minus Q plus 1 summation over I, rather it's Li, like for all I which is where the value of Li is greater than Q. So for every such I, you need to do this kind of thing, right? Now the problem basically is to figure out, if you are somehow able to figure out how many Li's are there which are greater than the given value Q, you can simply sum them all up and that will give you the correct result, right? So in this scenario, for Q equals 3, one way could be you can just sort this entire thing. For Q equals 3, you can, again, this 3 would come here ideally, but why I have put it here, I will come to that in a bit. But for now, let's say this is here. So in this case, you will simply do a binary search, come to this particular state, and sum for everything afterwards, you have to apply this exact same formula. And we know that this formula can simply be reduced to summation of Li minus NQ plus N, right? And summation of Li is simply something you can figure out using prefix sum here, right? So one simple strategy could be, take this entire thing, sort it, then do a binary search for every query. You'll get some index, sum everything afterwards, and then subtract minus NQ and add N. And you will get your final result, how many contiguous alternating sequences can be possible with the given length, right? And this entire thing you can do in simply log n time, because this entire array is something you can build beforehand. You can sort it and keep it ready beforehand as well. So during the query, you just simply are applying this binary search to know at which point you need to start summing up. And once you know that point, you can simply use prefix sum to get your final sum, right? So overall complexity is now order Q log n, right? Now this works, everything here works, except one small thing. The difference is with the last group. Why? Because let's talk about it. Let's say this is your current array 0 1 0 1 1, right? Again, as we discussed, because we need to take all sequences, we'll simply duplicate this array 0 1 0 1 1 and remove the last element because we don't care about length of greater than n. So in this scenario, we know that there are two sequences. One is this of length 4 and one is this of length 5, right? And let's say you need to figure out how many sequences of length 3 exist, right? Now if you figure out how many sequences of length 3 exist, let's start with the first one, right? So we have this particular sequence, right? This is a valid one, so we'll increment the counter. We have this sequence, again a valid one, so we'll increment the counter. We have this sequence, not a valid one, so we'll not increment the counter. We have this sequence, not a valid one, we will not increment. We have this sequence, valid one, we will increment. We have this sequence, valid one we will increment, but because this is something which is not starting before this index, this we can't consider because this is equivalent to this particular sequence. So you are repeating the same sequence twice, or you are overcounting. So to avoid that, you need to do some other trick. And notice that this trick is something you need to do for the last element itself. So if you think about it, there are two sequences, right? 4 and length 5. And if you count via the formula, both 4 and 5 are greater than 3. So the value would simply be 4 plus 5 9 minus 3 into 2 6 plus 3. Plus 2. So this will be your answer, or in other words, the value for this would be 2. There are two sequences of length 3 here, and value for this would be 3 sequences of length 3 here. So overall sum would be 5. But this 3 is not true. Why? Because in this 3, one of the sequence is this, which is valid one, but next is this, which is already counted in this 2. Similarly, the next one is this, which is also counted in this 2. So you can't count these two sequences here. So you need to remove those two sequences, and that is something you need to do for the last element only. Everything before is something you know that will start before this particular index itself, right? So what you can do for the last element, or rather the last sequence which is crossing this particular boundary, for that element only you will do some kind of compromisation. You will not add simply L minus Q plus 1 for this last element. Rather, you will check how many sequences are possible. Total 3 are possible, right? How many of them can be started before this index? So there are only one element or one index before this index. So just one can be started. The next one, the very next one will cross the particular index. So you will find two things. One, first, how many is possible? That is like L minus Q plus 1, right? How many can be started before the index, which is N minus L, right? Or rather N minus the starting point of the last sequence, right? And whatever is the minimum, that is something you will take, right? So hope this point is clear, that we need to do something extra for the last sequence, and hence in this particular original array I sorted everything except the last one, because the last one we will do something manual for that, right? So let's talk about it. So this is how the pseudo code would look like. What you are doing, you are simply querying querying for the given length. First, you figure out how many elements are there, because this n is something you also need to figure out, right? So this is count, which is n here. What is the sum of all the elements based on after the current index, right? It is less than, I think it should be greater than instead of less than. Sorry for that. Now after that, this is how your value would be, which is n minus 1 multiplied by q is similar to that. After that, for the last one you need to do something extra. So currently I have taken everything equally, so even the last one is equal here. So what I will do, I will simply check whether the last, whatever I have taken for the last one, if we have enough subarray that would be started before index n, and if that's the case, that's correct. Whatever I have considered is correct. Otherwise, we know that this many can be started, this many we have taken. So whatever is the difference, I need to remove that from the answer, because all of those will be starting after n, and all of those will be recounted again. So I'll simply subtract them, and that will be my final answer, right? So this entire thing can run in order log n time, given you can figure out this count and this sum efficiently, and both of them you can do using a simple prefix sum here, right? So we are able to solve this entire problem without the updates. Now let's talk about updates as well. So again, we'll not go to updates directly. Let's take a step back and let's assume that there are updates. So if there are updates, what will happen is something here would change. Let's say this would change to 0. Just an example. So in that case, what would change in your entire approach? In your entire approach, this 5 that you have taken or this 4 that you have taken will change, right? Will change to something else. And there might be new introductions of elements as well, right? So in simple terms, what will change here is this array that we have, there will be some element that will be removed and there will be some element that will be added, right? So even before coming to, like, if we need to go ahead with this approach itself for query part, we need to first make sure that we are able to remove and add elements to this array efficiently without compromising on this log n factor, right? If you are not able to remove and add elements here at all, then the query that you have figured out right now, this method, will not be applicable once you introduce updates, because once you introduce updates, these elements will be something that will be changing and you need to tackle that as well. So that's your first approach. Like, you will not jump to the update part directly, but rather you will want to test whether the query part that you have come up with is a valid query part or not. In other words, will it be able to sustain the updates that will happen as a part of the update query itself, right? So the update would happen to these elements. So there is a different story of how to even get this number after updates. That looks like a harder problem, but before that, let's try to figure out whether, if that happens, can our current update query work or not. So this is your update query. This is how your update query was, right? Now what would happen is, in this array we'll have some removals or maybe some additions, right? And you need to ensure that with each removal or addition, your complexity of this entire function would not change, right? So what you are doing, you were simply sorting this array, right? And if you remove some elements, let's say you remove 3 from here, again, let's forget about the last element for now, because let's assume that this element, you know that last subarray is something that you need to tackle by hand, so let's not worry about that. So what you're doing, you are simply sorting this entire thing and then taking a prefix sum to ensure that these two things are efficient. But as soon as you started removing things and adding things, your prefix sum will suffer a lot, right? Why? Because what we are saying is, let's say you add one more 4. So this 4 you can't add here, right? You have to shift these 2 elements and add back 4 somewhere here. You can maintain the sorted order using set, but then your prefix sum would be affected, because previously prefix sum was on this 5 and 5, considering this 5 and 5, but now there is a 4 in between. So everything after 4, the prefix sum for everything would change, and that is something you can't afford, because changing prefix sum would mean order and time, right? So you need to make this efficient. So I would encourage you to pause and try to think again for a moment. So the answer is simply, you need to maintain the sorted order. There is no workaround to that, because the formula that you have, which is L minus Q plus 1, this formula needs to be applied only for I for which Li is greater than equals to Q, right? So this is what you need to apply for, but you know that for this to happen, you need to figure out all the elements that are greater than a particular element Q. So sorting is something you can't compromise on. And what's the alternate, or what's the other way to keep the elements sorted? The answer is selection sort. Basically, if you know that all these elements has some range, instead of maintaining the actual order, you can maintain the count of elements in a frequency array and that will be equivalent to maintaining the array in the sorted order itself, right? So instead of maintaining this, we can somehow maintain this. What does mean? This mean that basically when you are adding, let's say 4, instead of like shifting everything here and then adding back 4 here, you will simply go and increment the count of 4 here, right? So let's take one concrete example. Let's say this entire thing was there, so you have 2 2s, so frequency of this part is 2. You have 3 4s from before, so frequency of this part is 3, and you have 2 5s, and rest all are 0, right? Now if I ask you, okay, give me the count of everything, or give me the sum of everything after you break them apart, you need two things. One, total sum of li for all I greater than q, total sum or total count of element after the index which are greater than equals to q. Again, why greater than equals to q? Why not li greater than equals to q? Because these numbers itself represent the actual array value, right? So what you need is, if q is equals to 3, what you need is sum of everything after this. So total count of element would be 5, and total sum of element would be 4 into 3 12 plus 5 into 10. So 12 plus 10 22. So those are the two things that you would need, and those two things you can figure out very efficiently with this particular array. And this updates as well, now you can tackle efficiently. You just need to do +1 and -1 to a particular index. So overall, what your updates are now, update is you are updating one particular index to +1 or -1, and what you need now is, you need count less than or greater than x, which is basically the count of everything in a range, and then sum less than equals to x, which in turn is also, like, let's say you maintain one more array which is just the sum of instead of 2 you will maintain 4 here, like 2 into 2 4. Instead of 3 you will maintain 12 here. Instead of 2 you will maintain 10 here, and so on and so forth. So basically this part would be the sum of everything after 4, this part would be sum of everything after 4 here, and both of them you can simply do using any range query data structure in log n time. Basically you have updates, point updates, and range queries, or range sum queries to be specific, and both of them you can do either using segmentary or fin tree. Again, if you don't know about segmentary or hearing the segmentary for the first time, there is a complete series on segmentary in this channel which you can go through. We have started from the very basic and have touched very advanced topics as well. So for this video you don't need anything apart from this first video itself, so you can watch that and you should be able to code this entire thing by yourself. Again, if you don't know about segmentary, just copy paste the segmentary code, treat this as a black box. Basically assume that if you want the sum in a range L to R, you can just call a function and get the sum, and that function will take only log n time. Just take that black box thing into mind and try to fit this into your code. So to summarize, what we have done is, we have started with this particular algorithm, and we saw that this algorithm works in q log n time. But if we start applying updates, our updates will look like, okay, I need to remove some element from here, I need to add new elements into here. So to tackle the updates, we saw, okay, this approach will not work, because this approach we need to keep elements sorted. That's one challenge. Second, we need to keep the prefix sums as well, and both of them is not feasible if elements are coming, like if you use set, you can't take the sum of everything after a particular value. Again, you can do it in set, but with standard set you can't do it. You can implement your own set, or you can use PBDS for that. Again, all of these we have discussed in the segmentary series already, but the simplest thing could be, you just use segmentary or any range query data structure to do this point updates and range queries, right? So with this, the count less than or greater than x would be log n, and sum less than greater than equals to x will also be log n. So this entire two things will still log n, and the rest of them are anyways order one time with simple mathematics. So overall complexity is still log n. which means we are able, if our update looks like this, like remove an element from here, add some new element from here and stuff like that, we can still query in just login time, right? So now is the time to introduce updates. So let's assume that this was your original array, right? And you want to process an update query as well. Again, with this array, I have assumed that you have built this like this kind of array already. So if you just look at it, this is the first sequence which is of size 2, second sequence of size 1, third sequence of size 1, and then fourth sequence of size 3, and afterward you can like avoid them as well, but I've kept that and tackle that in different fashion. But basically this is the array you have already kept with you, and this is not exactly what you kept. You actually have kept the frequency array that we discussed just a while ago and maintain a segment tree over it. So that thing is something you have already have. Now you need to understand, when I do an update, which of these elements I need to remove and what all I need to add and how quickly I can do that. And if we are able to do that part in login time, the entire problem can be solved in just login time. Basically every query is just login, so overall complexity would be q login itself, right? Now let's say you change this to 0, right? In other words, this element is now changing to 0. Again, not only this element would also be changing to 0 because they both were the same element at the end. So let's keep things simple and let's assume that these two updates are independent. So we'll take this as one update, and then whatever will be the updates here, we'll apply those, and then say there's just one more update this to 0, and whatever is the update, we'll apply them as well, right? That's the like broader strategy, because both of them are equivalent problem. We don't need to solve both of them together, right? So the first part, you need to change this to 0. So what you have is, if you change this to 0, what would happen? First of all, if the element was same, if let's say you have to change it to the 1 itself, nothing will change, update is done. If element value is changed, then few things would happen. Like if this is changed, now you have a bigger group altogether here. Previously you had a smaller group, which is this, and this, but now as it changed to 0, you have a bigger group which composes of all of these 4 elements itself, right? So in simple terms, if you look at it, this was your grouping previously: 0 to 1, 2 to 2, 3 to 3, 4 to 6, 7 to 8, 7 to 7, and 8 to 8. After this change, these 3 will be merged into one simple group, 0 to 3, and everything would remain same. In other words, what would happen is, you will remove 2, you will remove 1, you will remove 1, and add back a 4. So you are doing 4 updates to your original array. Original array was 2, 1, 1, 3, 1, 1. You are now saying that remove 2, remove 1, and add 4, right? So you are doing 4 updates here. 4 updates is fine, that's something we can afford, but can this go worse? The answer is no. This can't go worse, because what you are doing, you are changing something here, right? So this might be a part of a group, or this can be like alone at the end. Only these two scenarios can happen, right? If this is a part of a group, we'll come to that separately, but assume that this is not a part of group. In this particular scenario, that was the case. 2,2 existed in isolation. So because this is not a part of group, you know that what could happen? The worst thing that could happen is, I will take and merge the left and right into me, or either left or either right into me. That's the worst thing that can happen. You will never be able to merge 2 elements in the right. Why? Because you are sure that these 2 elements are separated because of this 3 and this 4, right? There was 0 and there was 0 here, or there was 1 and there was 1 here. That's why you have separated this 3 and this 4. Otherwise they are together already, right? Because they are separated with this 3, because you are changing 0, 3 is still same, right? And because 3 is still same, this separation would still exist. The same logic applies for the left part as well. This separation would still exist. Whatever before 0, 1 is there, assume that there is just one more pair before this. Whatever was there was separated because of these two elements, and these two elements are not changing. So this separation would still exist. So in worst case, what could happen is you will remove 3 elements and add back 1 element. In other words, you are doing 4 total operations in case of isolation. So if the element exists in isolation, that's what you will do in worst case. Again, this may not be able to merge, but that's the worst case. Now let's talk about the case where the element doesn't exist in isolation, rather it was already with some other element that has some other value, right? So for that, let's take this as an example, and let's assume that this was changed to 0, right? And if you think about it, this was existing with some other element, right? Now because this is changed to 0, it is sure that this will not exist with this element anymore, for sure, right? So what would happen is this would be broken into 2 parts, 1 and 2, and this 1, the changed one, can be either a part of this or can be a part of this. Now what's the best thing can happen, or worst thing can happen? Worst thing that can happen is this is now separated out fully, like this is 1, 1, and if that's the case, this may be merged with the next element as well. Like this can be merged with the next element as well. Again, you can't go beyond next element because of this separation, right? So the worst case is this is broken and this is merged with the next element. So what will change? Basically, you are removing something here, you are removing this as well, you are inserting a new one, and you are inserting a new one. Again, in worst case, you are doing 4 operation again if it exists with some other elements. So overall, what you are saying is, in worst case, whatever is the case, we will be doing 4 operation. And what's the operation? Operation is remove some length from here, like remove an element from here, or add some other element to here. And those 2 operations, we already took a look how to tackle that, right? So let's take one bigger example to make things a bit more clear before we dive into the coding part. So let's say this is your array 0, 1, 1, 1, 1, 0, 1, 1, 1, and as we discussed, we will repeat the same thing except the last element, right? Now initially you prepare this set and this array with you, right? Once you have these 2 things, now let's say update come. Again, if query comes, we know how to answer the query. That we already know of. We have taken a look a while back in this video itself. So let's focus on the update part only, and query part will you can define and watch that if you are still unsure of. So let's say update comes and update change this element to 0. Now again, as we discussed, this element to 0 basically means we are doing 2 updates. One, this to 0, and second is this to 0 as well. So let's tackle these 2 updates independently. So first we will change this to 0, and then we will call the exact same function. Let's say you wrote a function f for update, so you will call this function for this particular index, and then you will call the same function for this index as well, right? So let's say this is your function f transformation. So first we call the index for index 2, function for index 2, we change this to 0. Now what would happen? As we discussed, we will first go and figure out which group was this element a part of. This element was a part of group 2, 2. How to figure out this? You can simply do a binary search over this set. You can maintain this entire thing as a set and do a binary search over it, right? Student problem. Now once you have figured out which group was containing this element, you can simply try merging the left and the right of this group. Again, that's the worst worst scenario, but that's the very naive way you can do. You can assume that, okay, whatever is the case, they may be merged, so I will simply take left and right and try to merge everything, and whatever I will get, I will use that as an answer. So in worst case, what you can do is you can simply remove the contribution of this. Contribution of this was 2, so you can simply remove 2. You can remove the contribution of this. Contribution of this was 1, so you will simply remove 1. You can remove the contribution of this. So your contribution of this was again 1, so you will simply remove 1. Now again, these 3 might not be merged, but if it is not merged, I will simply add back again, just to keep the things simple. So now we have these 3 things lying around. We'll check whether they can be merged or not. So what you can simply check is whether these boundaries are not equal. If they are not equal, you can simply merge these 2. Again, after merging, you can check whether these boundaries are equal. If they are not equal, you can simply merge, right? So in this case, 1 and 2 indeed was not equal after update, so you can simply merge this part. Again, 2 and 3 again are not equal, so you can simply merge this part as well. So overall, you have merged everything. So in other words, you are saying that I will simply add back 4. So you have applied these 4 operations and you get this particular array. And again, these 4 operations you need to apply on this set as well. So this set you will again be removing and inserting ranges as well. So this is what you will have. Now, as I discussed, the second update would be like this. So you have to call the exact same function for index 7. What would happen is we have changed this to 0. So again, the same thing. You'll check which index this was, or which range this was a part of. This was a part of 7,7, right? So in this case, what is happening is you will say, okay, in worst case, what would happen is this and this can be merged. That's the worst scenario. So what I will do, I will simply, without understanding whether they can be merged or not, I will simply remove all of this. So remove this, which is remove 3, remove this, remove 1, remove this, which is remove 1. Now these 3 are independent. Now let's see how many can be merged. So 4, 6. So 4, 6 is this. Can this be merged? This was 1, and after update this will be 0. So they are not equal, so this can be merged. So this is 4, 7 now. Now 8 is 1, so this can also be merged, right? So overall you are able to merge all of this. In other words, you are saying that everything is now a part of one group, which is of length 5. So this will be your total updates for this particular iteration, right? Again, you can do this in a smarter fashion as well. You can avoid removal if it is not required, but that's your choice. In worst case, even if you do all of these, worst case instead of 4 operations, you will apply 6 operations, and that's also is fine, right? So this is how you will do the updates and keep your counter array valid. And once you know how, like, what all updates needs to be applied, you can simply use this strategy to keep your counter frequency array and your sum array updated. These 2 updates will be happening on a segment tree or any range query structure that you're using, but these 2 will be updated with the current exact state, so that whenever a query comes, you can simply go and fire these 2 things to get the final result, right? So if you have watched this point, I would strongly encourage you to pause and try to code this entire thing by yourself. Again, if you don't remember segment tree, there's a complete series on segment tree. You can watch that, or you can take the code and use it as a black box. For example, you can simply go to the code of this solution itself and copy this particular structure. This structure has 3 functions, which is query sum, query count, and update. That's what you need. You can simply assume that if you fire it for a particular index, it will give you the sum of everything after index x. If you fire it for a particular index, it will give you the count of element after this index. And if you fire this for update for this index, it will add this particular value. And again, this value it will add to both count and the frequency array as well, right? So it will update both this array together. So we'll come to segment tree part again, but let's focus on the main function. So what we did first, we first simply duplicated the array twice. Okay. After that, we build a segment tree of size 2 cross. Again, this 2 cross n is not required. Actually, you can simply build a segment tree of size n as well, but that's simply I did for ensuring, like, for avoiding one simple edge case, which will come to in a moment. After that, what we did, we simply group things together and put them in a set. So we started grouping things until, like, the last element that they have taken is not equals to the current new element. We'll simply group all of these and insert these finally to our set as well as to our tree. So both of them we will insert in this insert function. We'll come to insert function again. And once we have formed the group is when we will start answering the queries. So if you think about it, answering the queries are, there are two kind of queries. First, update, and second is the query, actual query. So update query, we know that we'll simply call a function f. In this case, this function f is update, which will take an index and will update its value to a given value. Similarly, I need to call update twice, right? For one for index and second for n plus index. So I will simply call the update function twice with the same value for index and n plus index. What about query? For query, if you remember, this was the pseudocode that takes two things: the length which we need to query for, and second thing is the pair that is crossing n, because we have to do some computation for that manually, right? So first thing is what is the length, and second the group that's containing x. This will give you the pair that is containing the index n, right? Now we have three functions to look at: one group containing x, then update, and then finally insert, right? So also count as well. So let's look at them one by one. So let's start with group containing x. That's the simplest one. So we have a set of all the pairs, right? What we can do, we can simply figure out the upper bound of index comma minus 1. Basically this will give me one of the two things. If let's say I need to figure out the, let's assume that this is your state, right? Let's say this is your state, and you need to figure out which of these groups contain 6, or in other words, let's say which of these groups contain 2. Okay, what you can do, you can simply figure out which group is starting after 2. So this is the group which is starting after 2, right? With that you can do with a simple upper bound. And once you figure out the upper bound part, either this will be the group which contain 2 or the group before this will contain 2. That's the only two scenario, right? So that's what we are doing. If it is not the beginning, I will expand it, go to the previous one and check if previous one contains the index. If it is, I will update to previous. Otherwise, whatever I got contains the current group, and we'll simply return that, right? So let's look at the update function, or before that let's look at the count function. That's very straightforward. It's exactly equals to the pseudocode that we have seen here, right? We will first count the total sum after index, total count after index. We figure out this formula L minus Q plus 1 summation. After that we have to reduce the duplicates. And how to figure out the duplicates? We will simply go over the last group and check whether we have, like, what we can have with the last group and what we taken with the last group. What's the difference between them? If there's a difference between them, we'll simply subtract those because those are duplicates, right? Simple. Now these three functions are remaining: insert, update, and remove. Let's look at insert. Insert is straightforward. We'll simply insert it to our set array, and we will update our tree as well with this particular count with a +1. In remove, we will do the exact opposite thing. We'll erase it and we'll update the tree with a value of -1. Basically, we are saying that at this count go and update, or at this index go and add -1. At this index go and add +1. Again, this +1 -1, it will automatically take care of adding back the sum as well. Basically, you are instructing it to add +1 -1 here, but it will automatically take care of adding and subtracting things from here as well. We'll come to that. Now The final thing is this if. Why this if is required? That I will leave that an exercise to you. This if is required because of this thing. I would encourage you to think about it by yourself. This is a very straightforward thing, and if you know about it, please post them in the comment section below so that I can also verify and others can also learn how you approach that. Finally, update function. Update function is also similar to what we discussed. We need to do two things, right? If it is already equal, we don't need to update. We'll just move forward. If it is not equal, then we have to update. Now, the thing is, we'll first figure out which group contains this particular index. Now, we'll remove that group altogether, right? After that, we check if like this is not required really, but anyways, let's discuss it as we have this in the code. What we check is let's say there's a L, there's a R, and there's this particular index I which you are updating. Now if this I lies between L and R and you are changing this from 1 to 0 or 0 to 1, then for sure you are dividing this entire thing into 3 different parts, right? Because if you change this, these 3 things can't stay together, they will be divided. So that's what we are doing. If like these are 3 different indexes, I will simply divide it into 3 parts: L to index minus 1, index to index, and then index plus 1 to R, right? And simply return. Otherwise, we know that whatever group that contains I either ends at I or either begins at I, right? One of these two are there. So basically it means that it can either be merged with the left part or the right part. Again, a simple optimization, but you can avoid this as well. You can simply take left and right irrespective and try to merge it as well, and that should suffice here. So what we are doing is, if it is coinciding with the left part, I will simply insert the right part. If it is coinciding with the right part, I will simply insert the left part. Now I will do upper bound again. This was not really required, but something that I thought of while coding. We will simply go and figure out the left part which can be merged. Then we will simply go and figure out the right part that can be merged. Again, this while loops and this thing, this entire part can be simplified. If any of you are interested, just try to simplify this entire part and paste your code in the comment section below. I would be happy to put in the actual solution as well. Now finally, whatever you decide to remove, you will simply remove it, and the insertion part would be whatever you have accumulated so far, that you will insert at once. So that's about update. Again, even this is a while loop, but this while loop will not go for more than 2 iterations or 1 iteration, that way, as we have seen, right? So don't worry about it. Now finally, segment tree, let's look at it quickly. We have 2 things, query sum, query count, that simply is calling the inner functions with the right bound as n-1 itself, right? And finally, this update is also calling the same function with the same values. Now coming to update, let's look at the update first. We apply the count accordingly, and then we apply the value accordingly, right? And after this, we simply do the usual thing with segment tree for both value and count. Now query sum is a simple update query, simple range query with tree count array. Query sum is a simple range query with the tree val array, right? So hope this entire solution is clear. If you have any doubts, feel free to post them in the comment section below. I would be happy to answer. If you like the video, give it a thumbs up and do subscribe if you haven't already. I will see you in the next one. Thank you.